Hi everybody, Physics Ninja here. Today I want to make a video based on a viewer question. It was based on one of my previously videos where I looked at how do you rotate an object around the origin. So we described this in terms of a two-dimensional matrix, and I showed you how to obtain that matrix to get the new coordinates of a point that's getting rotated by a certain number of degrees about the origin. The question from the viewer was, well, what about if the point is not at the origin? How can I describe the math behind that rotation? So today what we're going to do is I'm going to use this GeoGebra app here, and I'm going to put the link of the app that I'm using in the description. And what we're going to do is we're going to take this image of Daffy Duck. I've defined 2 points on that image, the point A and the point B that I've shown here. And my goal today is to pick a arbitrary point. In this case, I'm going to use the point -5, 4, this orange point labeled C. And my goal is to rotate Daffy Duck by 100 degrees in the counterclockwise direction. I'm going to show you how to set it up in matrix form. There's basically 3 steps you have to accomplish in order to do this. So we'll first do the simulation, and then we're going to show you how the result was obtained using matrix multiplications. Okay? Like with all my videos, if you like it, give it a thumbs up. Consider subscribing to my channel. It's the best way to support what I do. All right, let's get started. All right, so the way the app works, once I've defined a slider over here, I'm just going to pick everything I want to rotate. Okay? Pick Daffy Duck. It highlights both of these points. And then I just pick the point that I want to rotate, and I'm going to say 100 degrees, and I pick counterclockwise here for the direction of the rotation. And you hit OK, and it's going to create a rotated image about this point C by 100 degrees. So you notice the point A, which was originally at coordinate 2, 3, is now at -5.2 and 11.1. Coordinate B right here, which is at the other foot of Daffy Duck, it was at 5.1. It's now somewhere over here, -3.8 and 14.4. All right, so the goal of this video here is going to be describe how do you get to these numbers here for this rotated image about an arbitrary point. All right, the first thing I want to do, well, again, the goal will be to rotate this image here, rotate these 2 points, for example, around this point -5, 4. And I want to rotate by 100 degrees. So I'm going to do this in 3 steps. Here's the first step. Step 1 says you translate all these points back to the origin. Okay, and the way that you do that, well, you go to the point of rotation, and what transformation do I have to apply in order to bring this point back to the origin? Okay, in this case, the transformation is pretty straightforward, right? All you would have to do then is simply to add 5 and take away 4, right? That would bring this point back to the origin. So the way that looks like, for example, for these other points, well, let's just say this is a prime coordinate system here. So what I'm looking for here are what transformation do I have to get in order to get the new points, A prime and these 2 points. Okay, so all you have to do is you start with the original coordinate. For example, this one would be 2, and the y component here would be 3. So what transformation do I have to apply to the rotation point to bring it to the origin? Okay, you can see right away from here that the tx, the transformation that I have to apply to point C, will simply be +5 for this guy, and will be -4. That'll bring the point -5, 4 to the origin. So what you do now is you simply apply that to point A. So we started here with a 2 for the x component of point A, and now I want to apply the transformation. All right, so that means at the end I'm going to get 7 for the prime coordinate system. That's this point here. For the y component, you have 3, and then I want to do -4 as the transformation. I'm going to get -1. So at the end, this is my new coordinates for the translated point A. Okay, 7 -1. We can apply the same transformation now to all the points. So we're going to also do it for point B. What is bx prime and what is by prime? Again, the prime is just the translated points. So it's bx plus the transformation and by plus the transformation in the y direction. So here we started off with 5 and 1, and then I apply the transformation. And at the end of the day, I'm going to get 10 and -3. These are the points. Okay, so we've translated Daffy Duck by this transformation here, that's the first step. I'm going to show you how you can write the transformation in matrix form, okay? It's going to be more convenient for us later on when we want to apply all three steps just at once. All right, in this one, I just want to be able to write this translation that we had. We defined it as tx and ty, and we applied it to any coordinate. So let me just write it, for example, as this. Plus tx plus ty. And here, these are the primed ones, right? The translated new coordinates of those 2 points, x and y. Now, how do you write this in matrix form? Okay, what I'm going to do here, it's going to seem a little bit odd. What we have to do in order to describe a translation in matrix form is we actually have to use a 3x3 matrix. Now, this looks odd because it really is a two-dimensional operation, but it's just the way it is, okay? So we're going to describe this using a 3x3 matrix. So over here, we're going to define a vector. It has to be a 3x1 vector. I just add a number 1 here at the end. And that's just going to be to help us out. And now what I'm going to do here is I want to start off with x, y, and 1. Okay, so these are going to be the components that I start with, and these are the translated components. You're going to see why we have to go to this 3x3 representation. Because if these are the two equations that I want to matrix form, again, it has to look something like this. Think about it. 1, 0, and this I'm going to call tx. The next one will be 0, 1, and this is going to be ty, and the last row is very, very simple. It's just 0, 0, 1. All right, let's apply this transformation to that previous point. Let's just choose A, for example. I was looking for its prime coordinates that were translated. Okay, the matrix now is 1, 0. The transformation that I wanted to apply was 5 in the x direction, and 0, 1, and -4 in the y direction. So this is what the translation matrix looks like for that case. And here I started off with 2, 3 were the coordinates of point A, and then I just augment it with this additional 1 here. Now you carry out the multiplication of this vector in this matrix, and this is what we get. So here you're going to get 2 times 1 plus 0 times 3. I'm not going to do that one. Plus 5 times 1. So this here gives me 7. All right, the next one here becomes 2 times 0, 3 times 1. I've got to include that one. And then 1 times -4, that becomes -4. This becomes -1, and then the last one is simply going to be 1. So guess what? Now you just take the first 2 because these are the prime coordinates. So I have 7 and -1 are the new coordinates of the translated point A. Okay, so this is how you would apply this transformation. All right, before going on to step number 2, I do want to just find the inverse of this transformation. We're going to need this actually for step 3. Okay, but so if you write my transformation now, again, it's the same thing that I just wrote. I just defined that matrix for the translation by a 3x3 matrix I'm calling T. What if I wanted to find the inverse? So the inverse is something that takes you back to the original point. Right? So imagine now you started at the prime, then you wanted to go back to the original coordinate system. So what you want to end up at the end is this guy, right? Well, all you have to do then is just rearrange these two equations here. So you start off at the prime, and all I want to do is bring tx on the other side now. So I get minus tx. This one becomes y minus ty. Again, I can write this in matrix form, right? I can go x, y, and augment it with the number 1 like I did before. Here I can write x prime, y prime, and 1. And now the transformation matrix that brings me back is 0, 1. And look at, I just have to change the sign here. 0, 1, and minus ty, and 0, 0, 1. Actually, you can verify this. This is actually the inverse of that matrix T over here. And one way to verify is just to evaluate this product. T multiplied by this matrix here, the inverse, is going to be equal to the identity matrix. And you can also switch the order here. That's the definition of the identity matrix. All right, so this is going to be important. This is going to be the first transformation. For step 3, we're also going to use this guy, the inverse transformation, because I eventually want to bring that point back to where it started. Okay, well, I'll come back to that in a minute. Let's go to step 2 now. All right, what we want to do now is we want to apply a rotation. We're going to rotate it now by 100 degrees or by some angle theta here in the clockwise direction. So this was the topic of one of my previous videos. I put the link in the description, and this was the result from the previous video. I'm going to call the new rotated points now double prime. So really what we're looking for here are what are the new coordinates of both of those points. I'll just write it for the A point, but it's the same thing for the B points. All right, so what we have here is we started off here with single prime and AY prime. Okay, now the rotation matrix, if I'm rotating, now I've defined the angle to be positive here in the counterclockwise direction. Okay, and the matrix looks like this: cosine of theta, and here it's minus sine of theta and sine of theta. All right, so if I'm doing by 100 degrees, well, again, all you would have to do then substitute theta here equals to 100 degrees. The vector then becomes, there's nothing more than I started with 7, 1, right? And here would be cos of 100 degrees. This would be minus sine of 100 degrees, sine of 100 degrees, and again, positive cos of 100 degrees. And this would give me my new coordinates, A double prime, the X and Y components. All right, so this is what it looks like. Again, you can repeat the same thing for the B points. Now you just multiply this 2D matrix by this 2 by 1 vector here. So this becomes 7 cosine of 100 degrees minus sine of 100 degrees times 1. All right. And for the Y component, you have 7 times sine of 100 degrees and then plus cosine of 100 degrees. All right, we put that in the calculator, and I did that in the simulation here, and I got minus 0.2 and 7.1 for the double primed A components over here. And you do the same thing for the B components, and you get something like this. Okay, so this is how you can perform the rotation. Now the problem with this is I have my rotation matrix as a 2 by 2 matrix, okay? But we previously saw that the translation matrix, I wrote it as a 3 by 3 matrix. So what we have to do then is just rewrite this matrix here in 3 by 3 form, because at the end I just want to have one matrix that describes the full transformation. So let's write this rotation matrix in 3 by 3 as a 3 by 3 matrix. All right, to write this rotation using a 3 by 3 matrix, again, it's pretty simple. We're going to use the same kind of trick we just did before for translation. All you do is just augment it using a 1 over here. The 2 by 2 matrix doesn't change. All I'm doing is I'm just adding a 1 to this vector to form 3 by 1 vectors. So this here becomes cos of theta minus sine of theta. This is 0. This is still sine of theta. This is cosine of theta. This is still the 2 by 2 matrix. I'm just adding. There you go. Pretty straightforward, okay? So this is the 3 by 3 matrix that describes this counterclockwise rotation about this axis, okay? About this point, right? So we're going to use this later on for the full transformation, all right? So let's keep that one in mind. All right, and the last step here is we want to apply an inverse transformation. So again, our rotation point started out here. Again, after that initial transformation, we were rotating about the origin, the point 0, 0, and we want to go back to where my original position was. So the transformation that you end up applying here, again, it's the inverse of the first one that we did. So if you wanted to write this in matrix form, then it would be this, right? It'd be 1, 0, minus tx, 0, 1, minus ty, and then the last one, 0, 0, 1. This is writing the inverse transformation now in matrix form. And what I want to transform now are these double primes. So let's just start with point A. It's y component and the number 1. And at the end, we're going to get what our final value is. I'm going to call it triple prime. AY triple prime, and then the number 1. So now you simply substitute in our values. So what transformation brings us back over here in matrix form? Then that transformation would be, remember, this is going to be tx was 5, right? And ty was minus 4. So the way that this looks like then is 0. This becomes minus 5. 0, 1. This becomes plus 4. Right? Those two negatives multiply to give you a positive. All right, let's try it out for point A. So our double prime here was minus 0.2, and this guy here was 7.1. This gives me 1. And at the end, this is the last bit. Applying those 3 steps will get me these coordinates for my rotated point. So let's carry out this matrix vector multiplication. So you get minus 0.2 multiplied by 1. 0 times 7.1, and then minus 5. So this gives me minus 5.2 for the triple prime x coordinate. All right, let's finish off this. All right, for the y multiplication, you get 0 for the first thing. You get 7.1. And what else? Oh, plus 4. That's an easy one. That's 11.1. And for the last one, you simply get 1. So our final coordinate right here for this point A should be minus 5.2. Again, comma, 11.1. That's the final coordinate, okay? So that's applying the last step. All right, let's go summarize now the 3 steps. And I want to write things now down in terms of multiplying 3 3x3 matrices. And all of this full transformation can be written quite simply using this representation of matrices. All right, here are the 3 steps in matrix form. The first one was a translation, followed by a rotation about the origin, and then the last step was just a translation again, but it was the inverse of the first translation that I did. So what if we just wanted to write this all in just one matrix instead of doing these 3 different steps? So you start off with, well, what are we really looking for? We're looking for the last step, right? All right, I'm going to write it out as a 3x3 matrix. The first thing we do is, well, let's just write down this equation here for step 3. So we had the inverse transformation, 0, 1 minus ty, 0, 0, 1. Okay, now instead of writing this vector right here, right, the double primed, what I'm going to do is, well, here's the definition of the double prime. It's a matrix multiplied by the first vector, or by the primed vector. So let's go ahead and just write that. So we're going to write cosine of theta minus sine of theta, 0, sine of theta, cosine of theta, 0, and 0, 0, 1, multiplied by the primed vector. But the prime vector now is this definition. So let's go ahead and do this. So now it's just the original translation. Tx, 0, 1, ty, and 0, 0, 1. And now I still need that original coordinate vector. Ax, ay, and 1. All right, not too bad, right? So what we have here is, so this guy, this is the definition of the primed vector. If you combine it with this one, this is the definition of the double primed vector, all right? And then if you multiply the double primed vector by this inverse translation matrix, you get your final coordinates that you need. All right, now in order to kind of simplify this a little bit, what I'm going to do now is simply multiply these out, these 3x3 matrices. There are a lot of zeros in here, so it's not going to get too complicated. But let's multiply this out and just have one nice 3x3 matrix that you can easily apply to rotate any coordinate about any angle, okay? All right, we'll first start off just by simplifying the last 2. You can multiply either the first or second first, or the second and the third. It doesn't matter. I'll just choose it to do like this one. So let's keep this inverse translation untouched for now. All right, and now let's represent this by a 3x3 matrix. Okay, multiply 1 by 1, 0, 0 by all these rows. So this is pretty straightforward. This is cos theta, sine theta. That doesn't change, and that's also 0. The next one is you multiply this column by all the rows. So you get minus sine theta. You get cos theta. You also get 0. I'm going to give myself a little bit more space because the last one looks like it's going to be a little bit longer. The last one looks like this. So you multiply this third column of the last matrix by all the rows of the second matrix. So you get Tx cosine of theta minus Ty sine of theta. And then the last one, you can't forget this, and that's it. It's 1 times 0, so that's easy. Okay, not too bad. The second one now becomes Tx sine of theta plus Ty cosine of theta. Not too bad. And the last one, simply 1. And then I still have my original coordinate vector here. All right, so the last step now, we multiply these last two matrices. This is also going to give me a 3 by 3 matrix. Okay, so I'm just going through here. Again, this is just good practice for multiplying matrices. So cos theta 0. Oh, not 0, I'm sorry. Got to be careful here. Sometimes you try to go too fast. This is sine of theta. The last one is 0. This here becomes minus sine of theta. What else? Cosine of theta. So that first bit's pretty straightforward. It's the last one you have to be the most careful with here. Okay, so here we're going to have, again, the last column multiplied by each row here. So here you have Tx cosine of theta minus Ty sine of theta. All this gets multiplied by the 1. Then you get minus Tx over here. You get this extra term. Here you get Tx sine of theta plus Ty cosine of theta. And then you still get this 1 minus Ty over here. And then the last one is simply 1. That's straightforward. All right, look at this. This is really nice because I get one simple expression to describe this, to describe any rotation, right, about any other point, right? I start off with some point with x and y coordinates, right? The Tx and the Ty are the transformation to bring the point of rotation to the origin, and theta is simply the rotation angle. Okay, so let's go ahead and just apply this last matrix here and calculate, again, our triple primed, our transformed coordinates, okay, for point A. All right, so let's just apply it to just the case we just looked at in the different steps, but just in this combined form here, the shorthand. So again, the point A has coordinates 2 and 3, so that would simply substitute here. And the transformation was 5 and minus 4, and the angle was 100 degrees. All right, you carry out now this matrix vector multiplication. You get something like this, right? This is, oh, sorry, let's get rid of this. All right, so that would be AX cosine of theta. What else? Minus AY sine of theta. Okay, and then the last term now, I still have all of this, right? Plus Tx cosine of theta minus Ty sine of theta and minus Tx. All right, so now you could substitute in. I can group together some terms here. Let's, for examples, simplify this a little bit. Cosine of theta, there's two terms. There's Ax plus Tx. What else? For sine of theta, I get minus sine of theta. Here I'm going to get AY plus TY. Okay, and what else? The last one here, I'm still left with this minus TX term. All right, so now you just substitute in the numbers. So we get cos of 100. AX was 2 plus 5, right? Minus sine of 100. AY was 3. And TY was minus 4, okay, and then minus 5 for TX. Okay, I'll just simplify this a little bit. 7 cosine of 100. I'll have to use the calculator for this one, but plus sine of 100. Yeah, those negatives cancel out, and then minus 5. All right, put that in a calculator, and I get an x component for the full transformation now of minus 5.23. When I did it in steps, I just rounded to two significant figures here, minus 5.2. All right, for the y component, again, it's you get something similar. I'm just going to leave that to you, but you're just multiplying this vector by the second row of that matrix. You should get something that simplifies to something like this. It would be 7 sine of 100 for this case, plus cosine of 100. And this becomes multiplied by minus 1, and then plus 4. Now again, I put that in a calculator, and I had 11.07, which was approximately 11.1. Okay, so that is how you can apply a rotation about any angle and about any point, okay, at least in 2 dimensions. Okay, I did it using 3 steps. First, the translation, followed by a rotation about the origin, and then applying an inverse transformation to bring the point back. All right, hopefully you understood this video and you learned something. All right, we'll see you next time.